few weeks, whereas grains could have a shelf life if they are properly dried and stored, could be up to a year or 2 years, where you can store the grain without spoilage. But doesn't matter what food product is, when they go into the spoilage mode, they would produce the heat, moisture, carbon dioxide, and odorous volatiles. And these volatiles, and I think the best way you detect the spoilage in the food is by smelling. And when you are smelling, you basically are detecting those odorous volatiles being produced during spoilage of the food. And you can design sensors and nanosensors to basically detect, naturally, certainly heat, you can detect very easily. Or a sensor can detect the increase in the moisture content from the spoilage. Carbon dioxide sensors are available, which can detect the increase in carbon dioxide levels for the spoilage. But the odorous volatiles can be detected using sensors and nanosensors, which are typically looking at the grid of sensors. And they could be, a lot of them could be biological sensors, but in chemical sensors, where you would detect odorous compounds. Okay? So information from those could also be used then in the process automation or integrated with the image processing. And I already mentioned the pathogen detection, quite commonly done using the biosensors and the nanobiosensors. And that's the common use of the sensors in the agri-food industry. Another thing to keep in mind, in the food industry, typically you bring the raw material in, you then process the raw material, and then you ship the process goes out. And typically in the food industry, the logistic is that you bring first in, first out. So you bring the material, you process, and it goes out. What sensors can provide is basically enhance the understanding of the food material. So the first in, first out works very well if you have a constant quality product. You're not having any issues with the material as it is moving through the system. But you can have a batch start spoiling sooner. For example, you brought the raw material, and let's say you have a material lined up, but you brought material and you have a plan to process it over 3 months. And you could continue processing, but there could be the batch you brought, which is going to be processed 2 weeks from now, may start spoiling. So if you have the sensors embedded in the process, you could detect that spoilage or incipient spoilage. You can detect that incipient spoilage and say, rather than processing the first in, first out, maybe I need to take this material which is to be processed 2 weeks from now, bring that material first, process that, and then you go out of sequence. And that's what the sensors help you do, is that it allows you to improve the movement of products and processing plant, and it can be certainly improved by having the proper sensing systems. And one example I would give you is we actually installed a working with a tobacco processing plant in China. We installed a sensing system in the whole warehouse processing unit, and by that they have improved their they have reduced their spoilage or wastage by almost 20%. So they can process as soon as they get an inkling or they get a feeling that there is a potential to start the spoilage here, they would process that material first, and we're just using a first in, first out principle, and on that they were losing quite a tobacco in the process. And it was worthwhile for them to invest resources in the sensor technology to be able to detect that incipient spoilage and change that flow. So that's another thing to keep in mind when we are looking at the sensors and looking at the imaging, that we want to use that information to optimize the process flow, or optimize the flow of the material in the processing plant. Okay, so there are many examples which could be used for the sensors and as well as for the imaging, but sensors in particular. So here you see the examples are when we are talking about the food security, and particularly when we are talking about moving the food from farm to plate of the consumer. There are many places where you can use the technology. So the next few slides, I'm just giving you many examples where machine vision and sense could be used. So precision agriculture is one area, and I think you are familiar with the precision agriculture And at least some of you who would have taken some courses of pharmacy, where the idea of the precision agriculture is that you want to follow the 4R principle. That means is that you want to apply the right source of the nutrient at the right time, at the right place, at the right rate. So what this is referring to is the precision agriculture is that if you are growing the crop or growing the produce and you want to control the weeds, for example, so then you need, machine vision can be used to identify the weed plant in the growing crop. And then once you have identified the weed plant, you would then apply the chemical to kill that particular weed. So that's the herbicide you would apply at that location. If you don't have the technology, what you would do, you would apply the herbicide to the whole field. And it would kill naturally the weeds, but at the same time you're wasting a lot of herbicide because you're applying on the much larger crop area or on much larger field. Same thing would apply to not only for the weeds, but if you're going to apply the fertilizer in the growing to grow plants, there could be the areas of the field where you need more fertilizer because of the soil conditions are such that for whatever reason it is deficient in the nitrogen, for example, or phosphorus or potassium. So you would want to apply more fertilizer at that place. But the areas where it is sufficient, there is no reason to apply because the plant can only take so many nutrients. So if you oversupply, plant is not going to take it anyway. So it would be then leached into groundwater and have the damage on the groundwater quality. So if you want to optimize all that, you can use then the sensors and machine vision. So machine vision, for example, to identify the weed plant from the crop plant, as an example. Sensors could be used to identify the amount of nutrient level in the soil, and then using that information, then you apply follows 4R principle, which deals with the right source of nutrients at the right time, at the right rate, and right place. And so, which the case is referring here the field conditions. So you can certainly use that for decision making, and the whole area of the digital information which comes from sensors and imaging tools basically is driving the precision agriculture or the decision making process. Another area where this technology can play a role is in the traceability of the crop, livestock, or food processing sectors. So what traceability is implying, like if for example you were interested in making sure that you can show where that particular raw material came, and especially when you are applying the hazard principles, at that time you need to be able to know where the raw material came, so you know where that hazard came from, and you can take the remedial action at that point where the hazard is coming, until waiting to the point that if you don't be able to identify that source, then you have to eat a large quantity of material. Okay? And that applies to crop, to livestock, particularly in the meat processing. Same thing, like if you have tissues of the animals, you do the lab analysis and say this particular batch has a problem, you need to identify the source. So for the traceability, the sensors would play a significant role, and that then process continues for the whole food processing sector. Preferred supplier of safe, trusted, and nutritious food, that if you want to guarantee that to the consumer, and consumer to say that we supply you the guaranteed food quality, and you want to stand behind it, you would need the sensors technology or the imaging technology to be able to prove that you are able to maintain. So to build that reputation of a preferred supplier of safe, trusted, and nutritious food, sensor technology and image processing technology would help you achieve that. So you need to incorporate that in your thinking. At the same time, I think it has the potential to enhance the connectivity between the producer, processor, and consumer, because each one then has more trust built into the process, and consumer can relate to the issues the processor has faced or the processor has taken corrective action, and can show with the data that corrective action was taken, and the producers can show that right process was used. Another example would be this producer, consumer, and the processor chain would be example of the use of antibiotics, for example. The antibiotics are used quite significantly in the livestock industry, and that is causing problem for humans that they are consuming a lot more antibiotics, even though they are not taking antibiotics, because of products have large level of antibiotics, which then makes control of many of the disease infections very difficult to cure. So in that case, by monitoring properly, you could eliminate some of that risk or reduce that risk. Okay, some more examples. Infrared, and we'll talk about thermal imaging. Another term used for that thermal imaging is the infrared thermography. That could be used, for example, to detect the transport stress in the animals just before the slaughtering, because the meat quality of the meat quality is affected by the transport stress of the animals. So if you are bringing animals for slaughter and you can do the early detection, you can avoid that stress and then reduce and improve the quality of meat, or particularly the darkening of meat, and it becomes quite significant. Or even the illness in the animals, you can detect early by using the technology. Similarly, in the aquaculture, you can use the sensors and image process for detecting of the physical, chemical, and biological hazards, and that you would have learned through the HESA principles. Hyperspectral imaging, for example, we'll look at that, how hyperspectral systems work, can be used for determining the composition of food materials like protein, fat, and carbohydrate percentage concentrations. You can use hyperspectral imaging for detecting that. Sensors we talked about earlier, temperature, for example, body temperature of the animals. By measuring body temperature, like that, how like when we get sick, doctors would measure the body temperature and then try to detect the problem. Same thing can happen to animal. So by detecting the body temperature, you can do the early detection on the animal, and you can use both the physical temperature sensors, but also you can use the thermography, which is from a distance you can measure the body temperature. And I don't know at the time when there was a avian flu or H1N1 situation in all over the world, but I think in the airports, if you went to the airports, they were not even touching you, and there were infrared cameras installed in the airports where they were measuring the temperature as you were walking by, and you wouldn't even know that somebody is measuring your temperature. And if they detected high temperature, they would take the person away and then put in the quarantine. That was happening globally. Same technology could be used for measuring the temperature of the animals, for example, and do the early detection of the disease, so that you don't contaminate meat product during the processing, and a lot of other meat products get contaminated. And you can use the sensors and particularly image processing and machine vision for observing behavior and detect stress in the animals. And why you need to do that is because this then has effect on the quality after slaughter, quality of meat after slaughtering. So you want to minimize the stress for animals. Okay. Any questions at any time? You are all quite, hopefully not from the lunch, heavy lunch. This is an example where you could see the different stressors cause the kind of changes you would see in the animal rather than going through all of the stressors. For example, if you look at the social isolation and mixing of the animals, if you do the social isolation, it reduces the epithelial cell tightness, junctions, alter response to infections. The animals become more responsive or less responsive, increase the fear response, alters heart rate of the animals, decreases milk production. So if you go to all these stressors, you can use the technology to detect these stresses in the animals, whether it's using sensors or biosensors or nanobiosensors or image processing or combination of those. You can use that to detect these many stresses, so whether they are coming from transport, from feed deprivation, from thermal stress on the animals, or the weaning, when you remove the baby calves from the mothers, they feel the stress, and you can detect that using the restraint strain. So rather than going through all of them, I just want to give an example. There are many stressors which cause the changes, and those changes you can detect using the sensors and imaging.
So what parameter is usually used to measure this stress?
So the parameter, I think, to measure the stress, I think is you are looking at is the two possibilities. One is physical behavior. So in that case, you would use the machine vision, where you're looking at the animal start behaving differently than what you would expect in normal behavior. That can be detected by using cameras or image processing. Other one is stress typically results in the change in the constituents either in their saliva or skin, animal skin parameters are affected. And those again could be detected either using sensors or the camera. So because it's not measuring stress, basically is the body reacting to the external forces, and that you are basically trying to measure the reaction of the body. Some other examples, and this is continuing on related to the animals. So, for example, you can use the sensors for determining the sweat constituents from the animal, and the stress could be changes in the sweat constituents could be another way you can detect stress in the animals. Analyze sound, vocalization. So this is the ultrasound of the sensors which are based on the measurement of the sound signals. You can use those to again detect the changes in the animals which occur. Like pain would give you a different sound signal than we all experience that, or stress would give this, or the whining, or in the animals can detect that. Early detection of diseases could be, had mentioned that, detection of the virus, pathogens, and antibiotics can be done. Weight estimation for orthogonal images. So if you are marketing the animals, you need to go there to a certain size, but you are paid based on the weight of the animal. And right now, only way you can do that is that you have to take them to the corral and then weigh them, or how much they weigh. But you can use the two cameras where you can take a picture, one from the top, one from the side, and by analyzing the two images together, you can estimate what the weight of the animal is, and you can develop the relationship between the weight and so you don't have to basically disturb the animal. You can take those pictures in their normal activities and use that for estimating the weight. So and there have been research published in that area where people have tried to predict the weight of the animals, and analyzing the different components like saliva, urine, feces, blood, and then particularly using the sensors and nanosensors, you can get a lot of information about the raw material. So moving, any questions on this one before we move to the imaging? Okay. So the imaging is basically, when we talk about imaging, it is assessing the physical or chemical objects using spectral devices, e.g. cameras, and digital image processing to characterize objects for interest. So what is basically talking about is that it is taking the picture of an object, and from the picture of that object you are extracting the information. That's what would be referring to the digital image processing. You're extracting that information, and once you have that information, you use that information to make the classification or characterization of the object of interest. So that's like a simpler example would be like if you had a square object and a rectangular object and a circular object, you took the image, and then could you, just looking at the image like you could as a human being, but you now have developed a program which could take the information and say this is a circle, or this is a square, or this is a rectangle, and you would say that should be very easy. It is not easy. To give you an example, and I think I will give you some actual examples of images tomorrow. So if you can have a square and a circle which could have equal area, okay, because you can equal area of both. So you can just say that you can identify these two objects based on the area. Or same thing, you could have square or circle of the same perimeter. So you wouldn't identify, you can say that the perimeter would be different. But there are features features which you could use or characteristics you could use where you could identify. So one possibility is that you could say if you are only identifying between a square and a circle, one possibility could be is the if you took the radius from the centroid to the every point on the circumference, the radius would not, in one case be same, in another case it would have variations. If you have variation, so you have a variance, and radius might be the good way of identifying a square and the circle. So when you are collecting the features or when you are doing the characterization, you need to identify what would be the distinguishing features which would separate the objects. And sometimes, you, like in a square and circle, it's easy to visualize that how you could do that. But when you are dealing with the biological materials which are very inherently variable, you couldn't just say that this feature might work. So that's why you collect then a lot of features, a lot of characteristics, and using that many characteristics, you try to do the identification or classification. So the image processing is basically, and the reason to differentiate between imaging and bioimaging is then imaging is used then in the, I would say, automotive industry, in the electronics industry, whereas bioimaging is when you're dealing with the biological materials, where the variability is very different, the characteristics are different. So when you are assessing the physical or chemical object devices of interest, here bioimaging is referring to a dealing of biological materials, and that's the only difference, because the definition, as you see, is very similar, okay, in terms of the writing. But it's the one is dealing with the physical and chemical objects, and the bioimaging is the handling of the biological materials. So food materials, raw materials, processed materials, which have potential to be spoiled. Okay? Yeah.
Shape and size, right? What is the level of accuracy if I on the basis of shape and size, if I want to determine the weight?
Again, that would depend on the material. So it depends on the sample we were talking about earlier. So if your sample was robust and you collect the sample with the variability from the year to year, field, varieties, cultivars, and develop a relationship, so something like weight, and it would depend on the parameter, but I would say you can predict the weight by using typically the area, and you would get very good correlation.
Why I'm asking, yeah. Those like quality evaluation of cereals, particularly wheat,
yeah,
right, or semolina. We evaluate wheat, the boldness of the test weight is proportionally related to the yield of
semolina, yeah.
Right. So usually people have a, like in FCA people, they bring the test weight.
Yeah.
But they try to link it to the quality of the wheat. And sometimes you have the sprouted grain, get sugar, or sometimes you have the hailstone damage.
Yeah, yeah.
They try to link it to the yield of the flour or the yield of the semolina. That's why I was asking if I have a wheat, how much accuracy will have if I try to go it with test weight?
I would say it would have a quite high correlation, and because we have done some work particularly with wheat, and I think if I'm remembering, when we characterized, I think it was area gave almost about 70% correlation, and then I think when we added, there were 6 more features we added was the, and we will talk about these features tomorrow, the maximum length or the major axis and the minor axis. When you added few more features, the correlation went up to almost, I think, 0.9, if I remember correctly, 992 was the correlation. So it's quite high correlation. Okay. Any other questions? So the bioimaging, further clarification is that the when we are talking about is an artificial visualization, and that's what the artificial nature is coming by using physical camera or a sensor device, which could be an X-ray camera or thermal camera or high spectral camera. So that's the artificial visualization. Compare that to the human visualization. When we are seeing things, we are using our eyes to look at the material, potentially using a large spectrum. So rather than limiting to the visual spectrum, you want to use the as large spectrum as possible, rather than human vision, which is based on the visual spectrum. And so what you are doing is this, in that characterization is you are observing a material, you are capturing the image from that material, so you are capturing that information, processing that, and analyzing an object of interest, is doing the classification. So it characterizes complex size, shape, texture, color, and intrinsic properties of food, depending on what kind of sensors you use. Because if you were using only a digital camera or the camera in the visible spectrum, all you would get is shape and size. If you use color camera, naturally you would get color features. And a color camera can also help you give you the textural features, but even the color black and white camera or the monochrome camera can also give you textural features. And we will talk about what do we mean by textural features probably tomorrow, and how to measure those textural features. And intrinsic properties I already mentioned, either using X-rays or hyperspectral imaging, you can get those. And these then characteristics you use then evaluation of the quality of the food in an accurate and consistent manner. When you use these sensing systems, you basically increase the consistency and objectivity of the decision making. So it's no longer a subjective decision. And so when we talk about image, what are we talking about in the case of the image is a spatial representation of an object or a scene, and it is defined in terms of so if you take when you take a photograph, right now you are not seeing the pixels, but if you, and I think when you buy even your hand devices, they say that it is 8 megapixel camera, or it is a 4 megapixel or 12 megapixel. What it is talking about is the number of pixels they are in the image in that area. It is giving you those number of pixels. So each pixel really is the dot, or typically they are a square in shape. So these the image basically can be represented then as a function where the function is for each point, and each point then have a value. That value is basically the reflectance value, or the light or intensity of the light being reflected from that object. So it can be represented as basically a two-dimensional function with the magnitude at each point or each pixel being the gray level. And if you were using a color camera, you would then possibly have 3 values at each point. So one would be for red, and one for green, and one for blue, which are 3 primary colors. And using those 3 primary colors, you get all other colors which we see and visualize and interpret. So that's how you represent the image, and you then extracting all of the information from that XY matrix or function. And that's what we would do, how we extract that information tomorrow. So in the bioimaging, when we are talking about doing simple process is simple. You want to take a picture. From that picture, you want to, in the olden days, you have to digitize it, because typically you would take an analog signal, would be analog. Nowadays, digital cameras do that digitization, built-in digitization. So you digitize that image, and you basically have for each pixel in the image of interest, you have a gray level value, or the light intensity basically, or it could be intensity in the light intensity I'm saying in the visible range, but if you are NIR range, it's the same thing, you are still measuring the intensity at that wavelength. So the wavelength strength is the value you have. From that information, then you want to extract the information. So to extract the information, the steps involved are, so image acquisition, so acquiring that image. Then you want to do the image pre-processing and age enhancement. So what is the pre-processing? Pre-processing typically is, so when you take the image, sometimes there could be a pixel. So like for all of the surrounding pixels are, let's say, and for time being 100 is the value of the reflectance or light intensity. But there's one pixel which has a 0 or 5. There could be, so that you would say that this really doesn't make sense. So that could be because there's a dead pixel in the camera, so camera may have a defect, or the object may have had some damage on it, and that would have caused it. So you would try to do the quick analysis of the image, and typically that is done by a process called filtering process. So you would use different filters and do the analysis, and you would do the basically cleaning of the image would be the best way to say. The cleaning of the image, removing the depth pixels, anomalies for the image, that's what would fall in the pre-processing category. Then enhancement of the image would be another step which is used in processing, where you are removing the blurring of the image. There could be distortion in the image, so you basically remove those or correct for those, would consider enhancement. Segmentation is so you have the image, and you could have object image, but object is sitting on a background. So like you could have a black background or white background, and you might have 4 or 5 objects sitting on that background, and you take a picture, there would be a lot of white background pixels would come in there. So you have to separate the object image from background image. So that's what is referring to as segmentation, and we talk about how to do that. And the representation of the object, and here you are basically trying to identify. So an example, like if you had 5 kernels sitting on this 5 kernels of wheat, or any 5 objects sitting on this platform, which is the black platform, you took a picture, but you still have to identify that there are 5 objects in this image. So that would be the representation of the object. So how you do that there are 5 objects in this image. So do the labeling, it's referred to as labeling exercise. And you can do that by either going boundary, so you can go follow the contour of the object along the boundary, or you can do by the region growing. You start from point and growing that, and then you cover the boundary, and then you give a specific unique label to that. And then is the description of the object, and so that description basically is referring to is how you label that. So is it object 1, is it object 2, object 3, object 4, and then once you have that information from the description, is also referring to extracting features from the objects. So the features would be shape features, size-based features, color features, textural features, or the histogram features. So any of the features you extract, so you're trying to describe that object. And once you have that information, you then do is the recognition by first you do the training of the classifier, and then you do the recognition. So these are basic steps involved in the bioimaging or an image processing field. Okay. Any questions on any of those terms? And a lot of these would be clearer also when we go through a little more detail in these. But steps make sense intuitively. That's what you do. You take a picture. You need to find out what's in the picture. Once you have determined what's in the picture, you want to characterize those objects. What is the information you get from on those objects? Once you have that information, you then develop the library or database of features, use them for training, and then when an unknown object would come, you would compare with the data basically in the database, and then do the recognition. Okay. So I was talking about the contaminations which can occur in the food industry, the physical, chemical, and biological contaminations. So examples of physical contaminations in food would be presence of dirt, metal, glass, pins, and plastic, bones, or anything other than desired product or food product would be the physical contamination. And typically you would use the X-ray based system, especially depending on the food product. Like if it is a grain, you would basically would be using the visual pictures. You can use those to detect dirt, for example, on sample, or the physical objects which are not grain by using image processing. If it is processed product, you would have then used all the X-rays, and X-rays are commonly used for detecting of these materials in the product or in the meat product. Typically, you would use this, or in packaged food, you would use X-ray because you are looking at internally the packaged material, for example. Okay, so depending on material you're dealing with, different kind of sensor would be used, or sensor I mean is the camera or the visible spectrum or the range of spectrum you would use. You're looking at these kind of contaminants you can detect using the system. The chemical contaminants typically would be in the food, as you would know, would be pesticides, insecticides, herbicides, larvicides. Sometimes even the cleaning supplies get into the food product, which are used for cleaning the floors, and the processing equipment can get into the food process, cleaning supplies, or any other chemical product which is not supposed to be present in the product would be the chemical contaminants, which you need to detect and protect against. Consumer need to be protected against. Biological contaminants you would find in foods. It would be insects, pests, insect parts, or pest parts, mold and fungal infection, pathogens, and bioterrorism agents, which could be present in the food product, and you need to detect. And that's what these systems are allowed to do that. And there are other contamination issues which you find in the food products. Or the product is spoilage due to undesirable atmospheric conditions, such as high, low temperature, moisture, humidity. So these are not contamination from external sources, but these are the contaminants which food itself can produce, and you need to be able to detect that, and again protect the consumer against those contaminants. Okay, so the electromagnetic spectrum then I have mentioned a few times. So we look at is the most of the cameras, or most of the human being deals basically in the visible spectrum. So if you look at overall spectrum going all the way from gamma rays to radio waves, visible spectrum is a very small component of that. Okay, in terms of the nanometers, so you are looking at typically the visible spectrum is 400 to 700 nanometers in terms of the range. You are looking at the physical range. And also when you go from gamma rays to the radio waves, what you see is so wavelength is increasing when you are going from gamma to radio waves. So you have a short wavelength for the gamma rays and the high wavelength for the radio waves. Gamma rays, on the other hand, have very high energy, and so that they can penetrate quite deep in the product, whereas radio waves have low energy, and so they can't penetrate to the same depth. And the frequency is high on the gamma ray side, and it's low when you go towards the radio waves. In the image processing, typically I would say that the visible is the most commonly used. The next to visible is the near infrared. So near infrared is also quite significantly used, because as you look at the spectrum, there's a lot more variation in the product when the NIR range or near infrared range, just outside the visible red infrastructure, and that's where also is the thermal cameras are based on, or the thermography is also based on that, and then NIR, near infrared, is referred to as that heat part of the spectrum. Okay, so the visible NIR are probably the most commonly used, and then I would say the X-ray would be the third one in terms of the use, and particularly detection of the contaminants, the physical contaminants, especially when you're looking at the objects inside the food products. X-rays are commonly used. So a lot of work in terms of imaging would be done in the visible spectrum, NIR spectrum, and X-rays. And hyperspectral, when you do, for example, when you are taking an image using the camera, and you are getting a value, you are basically getting a gray level or the intensity of that image. Whereas in the hyperspectral imaging, you can look at each pixel can give you a spectrum. So there the data becomes, and rather than a two-dimensional data or a matrix of the data, it becomes a hypercube. So you get a lot of data because each pixel can have its own spectrum, and you analyze that information. So in terms of the spectrum, basically you're looking at X-ray, visible, and NIR, but hyperspectral would be used in any of those ranges. You can do hyperspectral visible spectrum, you can do hyperspectral imaging in NIR, or you can do from visible to NIR or visible to IR, or in X-rays. Hyperspectral is not a spectrum, but it's looking at the information in a different way. That's what the hyperspectral imaging refers to. So the three critical wavelengths which are used for detection of the food characteristics are visible, NIR, or maybe some IR, and the rest of it is X-rays. Okay? So why we want to use the bioimaging? Some of it I may have mentioned a few times. It is that we want to measure is the quality of the food and agricultural materials, and right now, a lot of that quality is monitored by the human inspectors. So the human inspectors bring inherent limitations. They bring inherent high processing power also, because as I was giving examples in the morning, they can process the information very quickly, and the computers, even though they are very fast, still not as fast as human brain works, because we were talking about billions and billions of calculations per second. So still the processing is done, and the processing is done differently in human brain, but there are still some limitations. So human beings, when do the analysis, they would give you the results are still subjective, and one inspector, even after consistent training or long training, still may give different results. So that subjectivity is still there. Results by the same inspector, sometimes if you give the same sample at different times, they may not give you the same results every time. So there's inconsistency in the human inspectors. It's a tedious job. People do get tired, and that lead to the inconsistent results. They are human inspectors, although processing of information is fast, but process of complete decision making is quite slow, because they have to spread sample, separate it out, make the decisions, and imaging could hopefully do that faster than that. There's a possibility of cross contamination, whether the human beings could make the samples where the cross contamination can happen. Fatigue and tiredness would affect results. Depending on physical condition people are, would have different results. And we want to automate the process. Human beings, they can't be part of the automated process, so they cannot be used in the online monitoring. Human beings are expensive, even though when you look at the initial system to buy a camera system or imaging system to do, and you would say very expensive. But it's, when you compare that to the camera working for a year, compare the salary of the person doing that for a year, okay, then they are not expensive. So human beings in that sense are very expensive. And an example I'll give you here is we were working on designing a robot system for so in Canada, grain moves in bulk, and the grain comes in the rail cars to a terminal elevator where the grain gets dumped. And there a human being basically opens the rail car gate, and so when they open the gate, grain would start falling. So when they open slightly, what they are looking at is, does it have a wheat, or does it have a barley, does it have canola or pulses or whatever it has. They are making that decision, and if it's making, so once they know that it is that particular grain, then they confirm that that's the information on the information receipt on the bill, which is the information about that real car, that this should have wheat in it, this should have barley in it. So they confirm that, and if that confirmation happens, then they basically open the gate fully, and then they dump the grain. We were so replace the human being. And why? To give the reason I'm giving the example is the cost. In Canada, that person was costing $90,000 a year. So if you are running 3 shifts and making sure that people have time for vacation and the sickness, so you need 3 shifts means that you need minimum 3 people every day. They only work 5 days, so you need to allow for the weekend. So you need extra person to cover the weekends, extra person to cover the sickness. So the total number of people to operate that one robot system, later on got 9 people involved. Okay, so we were working to design a robot which could do basically the same thing, because it can then open the rail car gate and close the rail car gate. That would be designed. We had designed a machine vision system to be able to, when the robot opens the rail car gate slightly, and you take that sample, you analyze that sample, and then say, is it wheat? or is it a barley, or is it pulse? Confirm that with the information on the bill. And then the robot can open and close the gate. The Sun robot then can work basically 24-hour days. So the 9 people's salary versus one robot system, you can spend a lot of money on designing the robot, and it still would be way ahead after almost about a year. And within a year, you can pay that robot many times. So that's and that's why the automation pays in the long run. It is capital intensive at the beginning, but it becomes cost effective in the long run. Now, you would, and again, we can argue that then you have to take the social aspect into consideration. You are placing 9 people. Is that in the best interest of the society? And it depends on the societal conditions. There are times when you would say it's not a good idea. Other times you would say if there is a shortage of the labor, if there is a shortage of the manpower, then it would make sense to replace that. Okay? So they are expensive. Human beings are very expensive. Tea ready? Okay, we can take a break. Okay, so we will take a break. We will come back